We have found a new particle never seen before in Mother Nature.
What happens when humanity splits a singularity and tears open the fabric of space-time twice? You're here because you know the name CERN isn't just about physics. It's about pushing the boundaries of creation itself. In this video, we'll reveal what happened inside CERN's collider that night, why scientists fear what they unleashed, and what may have slipped through reality's cracks. Using leaked data, physicist testimony, and radiation signatures that defy known science, we'll piece together the chilling truth. First, the split itself, then the impossible signals, the vacuum code theory, the particle that shouldn't exist, and the consequences scientists didn't anticipate. The night they split the impossible, it began as a quiet, after-hours run at CERN's Large Hadron Collider, a high-energy configuration that wasn't on the public schedule and wasn't even known to most of the staff. Only a skeleton crew remained in the control room that night, monitoring as the collider pushed far past its usual operating limits. The official goal was to study particle interactions at unprecedented energies, but deep in the minds of the physicists present was another question: how far could they go before brushing against the limits of the universe itself? What they found went beyond any simulation, any theory, any safety calculation they'd ever trusted. The detectors lit up with a signal so alien to the expected results that one physicist first assumed it was a system fault. In the collider's heart, two streams of particles had smashed together at energies previously deemed unreachable. The result was not just another high-energy collision. It was the birth of a microscopic singularity, a black hole smaller than a proton. Normally, such objects are fleeting, vanishing in less than a billionth of a second through Hawking radiation. But this one didn't behave as physics predicted. Instead of collapsing instantly, it did something no black hole had ever been seen to do. It split. This was not a collision. It was not a decay. And above all, it was not one of the things that was so lovingly described in their equations. Within the blink of an eye, two singularities were halved, each one half the mass of the original, but somehow glowing with twice the brilliance. The datacast turned red, and emergency protocols came into play. The radiation reached spikes that the collider had never had to shield itself against. Within the chamber, temperatures rose to those expected in the early moments after the Big Bang. Even hardened detector components began to warp under the torrent. In those 0.003 seconds, the rules of reality broke down. Gravity in the chamber did not behave as dictated by Einstein's equations. Space itself flickered, as though the constants that anchor our universe were momentarily rewritten. The physicists stood aghast as their instruments captured a once-in-an-eternity transformation of the most fundamental object in the cosmos. To split a singularity was not merely improbable, it was supposedly impossible. One of the researchers later likened it to taking the lock off the universe and then pulling the door open from both sides. If a singularity is nature's ultimate boundary, a point where physics cannot speak, then cutting it in two was like forcing open a second entrance into a place no one is meant to see. And through that entrance, something seemed to be stirring. And then it was over. Dead silence enveloped the detectors as the singularities vanished. However, the readings told another story: anomalies in radiation patterns, bizarre readouts in gravitational measurements, and unrecognizable signals pertaining to various particle decays. In the hours and days that followed, the realization sank in. They had not only split a singularity, they had reconfigured the conditions of reality, if only for a split second. Answers were not available. Only the lingering conviction that something odd had taken place tortured them. The clue was buried deep among terabytes of data collected, a signal refracted through the chaos, hinting that what splitting the black hole had done was also throw something to the edge of the world. But it wasn't just a split that shook physicists. It was what the split seemed to be whispering from beyond. The code hidden in radiation. When the immediate chaos in the collider chamber subsided, the incident was already being labeled as an impossible event in CERN's private logs. But the true mystery wasn't in the melting components or the emergency shutdown. It was in the patterns buried inside the radiation data. Normally, Hawking radiation from a black hole is random. Its particles are emitted in a chaotic scramble with no discernible order. That night, however, the detectors recorded something else entirely. Instead of meaningless noise, the radiation came in pulses, structured, repeating bursts that formed a mathematical rhythm. Each spike in the data had an almost metronomic precision, separated by intervals too exact to be random. At first, Researchers thought it might be interference from equipment damage during the incident, but multiple independent detectors, shielded from each other and running on isolated power systems, had logged the same sequence. This wasn't a glitch. The physicist Dr. Elena Costes from MIT would subsequently call it a coherent emission, which contradicted the black hole information paradox. According to Stephen Hawking's original theory, information falling into a black hole is lost forever, either trapped beyond the event horizon or scrambled into jumbled states of meaningless static. But this was suggesting something far more disturbing, information making its way out intact from the split singularity. The emission structure suggested that the two singularities created in the split were somehow interacting with one another. Their energy outputs seemed to amplify one another in a curious kind of feedback loop, where one pulse from one singularity would trigger a stronger pulse from the other and back again. This self-sustaining cycle, lasting only a few fractions of a second, produced local bulges in the gravitational fields and even transient perturbations in electromagnetic properties in the chamber. The instrument recorded fluctuations within the vacuum, as if space-time itself had managed a brief resonance like that of a bell having been struck. Merely a feature of physics of the experimenters dealing with the data. To them, these appear only like something more than a coincidence. The regular recurrence of these signals looks suspiciously like a coded message, intervals of the pulses, followed by prime-factored series, energy intensities mapped symmetrically curved. If it's a coincidence, it's probably the most elaborate and unlikely coincidence in the history of experimental physics. More than a couple of the boldest theoretical physicists dared whisper the obvious but dangerous thought: what if this pattern was a signal? Not, of course, a signal like a standard radio transmission, but direct information encoded in the radiation, a message not sent through electromagnetic means, but literally by the decay of singularity itself. The idea is nearly too outrageous to consider, yet the information stolidly stated it. Some were increasingly disturbed by the implication that the radiation source may have lain somewhere else entirely, not bothering to analyze from what position an observer could have seen the singularity. If the split had momentarily torn open an exit from the labyrinth, radiation could have been sculpted by whatever lay beyond that tear. This means that the oscillation may have acted like a bridge to conduct knowledge from elsewhere into the domain of our detectors. This was no longer merely a matter of anomalies that an experimenter might find interesting. It was an actual matter of contact. The signatures in the data constituted something akin to an outside whisper that drifted through this universe by way of a minuscule crack. If that radiation was a message, the next discovery suggested it was written into the operating system of reality itself, cracking the vacuum source code. At first, the idea sounded like pure science fiction, more the domain of speculative philosophy than hard physics. But as CERN's analysts dug into the post-event readings, an unsettling picture began to form. Space itself, it seemed, had been altered, not in a dramatic, cataclysmic way, but in tiny, measurable changes that should have been impossible. Gravity in the detector chamber had briefly weakened by 0.5%. The decay rate of certain unstable particles had spiked far beyond predicted values. Even time, measured by the most precise atomic clocks, stuttered by a few microseconds before returning to normal. Such variations shouldn't happen. The constants of nature, like the strength of gravity, the electromagnetic force, and the speed of light, are supposed to be immutable. They are the bedrock of reality. And yet, during those fleeting instants after the singularity split, that bedrock shifted. If the readings had more or less confirmed the theory hovering at the fringes of modern physics for many years, it was that space itself is not really empty. Rather, it is structure. It is a surging, encoded field containing the operating instructions of the universe, ways by which physicists refer to it as a quantum vacuum, a seething sea of energy fields fluctuating in virtual particles suddenly popping in and out of existence. Some theorists, however, go as far as this phenomenon. Fluctuations follow sets of supposed source code of reality. In normal times, such code is untouchable. An incredible event, then, occurs when a singularity is actually split, the ultimate breakdown point of space-time. Some, indeed, hold that the event functioned like a sort of backdoor into the programming of the universe for a very short time, allowing overwriting of the constants. It would seem that for 0.003 seconds, someone reached into the engine of reality and adjusted the gears. Dr. Lisa Randall, a foremost quantum field theorist, bluntly put, we detected fluctuations in the vacuum state, which could only be described as such. It's as if the fundamental rules were momentarily altered. The alteration had to be timed. It occurred precisely when those strange, structured pulses of radiation were recorded. The implication was that whatever that pattern was, it might have been interacting with, or perhaps even rewriting, the vacuum's code. Now, picture reality as a simulation in the sense of digital, computerized simulation, but as running on a fixed set of mathematical laws. Now conceive of an event so extreme that it will edit rather than just bend those laws, an occurrence for which that 0.003 seconds might have operated under an entirely different rulebook, rules in which our constants and forces were not the same as those in the rest of the universe. Having asked a question that, perhaps, might be termed outright dangerous, a few researchers muse upon the possible consideration. Given that one could change a vacuum code for a brief span of time, would it not also be possible to deliberately change it for one's own ends? Could we ever change the parameters of physics itself? The very idea was intoxicating, and so, too, was a terrifying realization. For if the splitting process had been able to expose a code surface of reality, maybe it had been imprinted or rendered incapable of protecting itself from further exposure. And so, in this thin moment of opportunity, something never witnessed before occurred. The detectors did not just report modifications of constants. They also registered the birth of a particle so exotic it was not supposed to exist in this universe at all. The particle that shouldn't exist. When the initial shock of the split subsided and the team began combing through the particle data, they expected to find the usual debris from high-energy collisions, quarks, leptons, and familiar decay products catalogued in the standard model. Instead, buried in the noise was something no one had ever seen before, a particle cluster with properties that didn't match any known category. It was heavier than predicted for its composition, oddly stable for its energy state, and carried a slightly unusual charge. The more they analyzed it, the more unsettling conclusion became. The readings matched theoretical predictions for something physicists had long feared but never observed, a strangelet. In simple terms, a strangelet is a hypothetical particle made of strange quarks instead of just the up and down quarks that make up normal matter. On paper, a stable strangelet could trigger a chain reaction, converting any matter it touches into more strange matter. The process wouldn't be explosive. It would be silent, atom by atom, spreading like a slow, unstoppable infection until everything was transformed. It was proposed as a worst-case scenario back when particle collider plans were just being laid. Safety reviews done at CERN and other places dismiss the danger as virtually impossible in normal collider operation conditions. Energies larger than that were considered as unattainable, and even granting the formation of a strangelet, it would most probably be unstable and decay almost instantly. But the singularity extraction was not a normal collider event. It had briefly changed the rules of physics inside the chamber. This was bizarre nonetheless. In those altered conditions, something impossible happened. A strangelet appeared for a full 17 milliseconds, an eternity at the subatomic scale, before decaying harmlessly. However, the very fact that it existed, albeit briefly, was sufficient to shake the scientific community. The very fact that it formed suggests our safety calculations may no longer apply when we change the constants of nature, says particle physicist Dr. Helen Schmidt. The implications were horrific. Inside a controlled experiment, strangelets had been made unstable in some way through the forcing of fundamental physics to obey different rules. With a slight alteration to the charge of the particle, or had the same conditions been sustained even for a fraction longer, this would have led to disastrous consequences. No explosion, no flash, just a quiet transition from one state of matter into a new, strangely different one. To laymen, it may sound like science fiction. To the scientists who knew their physics, such scenarios served as reminders that even the most remote risks can become real when tampering with that which one does not know. The strangelet was not simply an oddity. It was a harbinger that in the altered reality of the collider, an avenue to unaccounted-for phenomena had been opened. In the words of one physicist, later, one can compare seeing the data to watching a mythical predator walk across your front lawn, proof that the stories were true and that this thing knows where you live. Within milliseconds, the strangelet could have died, but that served to show that the altered vacuum state created by the split could give way to matter that simply ought not exist in our universe. As soon as the team had the collider down, they also quickly learned that all this was no longer risk-free. Upon separation of the singularity, indeed posed a decay of the strangelet. The strangelet was said to produce side effects that would no longer be restricted to the lab. But even that wasn't the end. The most haunting consequence wasn't inside CERN's walls. It was out there, in our world. The ripples across the planet. In the hours after the collider shut down, CERN's internal focus was on containment, ensuring that no residual radiation leaked from the chamber, verifying that no lingering anomalies persisted in the detectors. By morning, the facility's official statement described the event as a data irregularity during controlled test. But the truth was far stranger, and it was already spreading far beyond Collider's underground tunnels. Around the world, independent monitoring networks began logging peculiar readings. In Japan, a network of atomic clocks, synchronized within billionths of a second, reported an unexplained phase drift. At almost the same time, a satellite over the Atlantic registered a fractional drop in local gravitational strength, far too subtle for a human to notice but unmistakable in the satellite's precision instruments. Across Europe, low-frequency electromagnetic arrays picked up transient pulses, unlike any known atmospheric or cosmic source. None of these irregularities lasted long. Most lasted for less than a second and did no harm. Pulled together, however, those anomalies told a rather dark tale. Whatever had happened in CERN's chamber had not remained in CERN's chamber. The after-effects, however faint, were indeed measurable. The singularity split had sown weak ripples through the very fabric of the physical constants defining this planet. As soon as these outputs reached the farm of senior physicists, the depository stock debates erupted. Some people preferred to stick to conventional explanations: instrument malfunctioning, uncorrelated coincidence, rare atmospheric interference. Others consider something very deep, perhaps the evidence that the singularity split has momentarily coupled the altered vacuum state of the collider with a wider universe. In plain terms, this could mean that the tear in reality has not closed fully by the time the singularity's coherence disappears. A strange theory began circulating around theorists familiar with higher dimensional physics. The theory is that, according to exposure the interface, perhaps a singularity of black holes is not purely the point of infinitely dense docking density, but actually a segment where our universe, in 4 dimensions, brushes aside another, more dimensions. By splitting the singularity, the experiment could have opened a temporary leak through which information, energy, or even matter could enter. Or, more likely, these traumas can perhaps be tiny stigmas around the globe, the flitting changes in the constant of reality propagating backward and diffusing out further. Then the very existence of such phenomena implied that boundaries among different realities were more scrutable than anyone had had the guts to think. And if something slipped through the crack onto our side to edge it out, it might not leave the same way it came in either. Weeks passed, and the anomalies ceased, or they just ceased to be noticed. Some researchers continued their quiet monitoring, instruments tuned to read the most minuscule vibrations. They weren't looking for just another spike in radiation or gravitational anomaly. They were looking for patterns. Because if the radiation pulses in the collider had been messages, then perhaps the leak had allowed for two-way communication. One physicist said without revealing his name, "We opened a door, and we do not understand it. We do not know whether it is closed, and we do not know whether something on the other side saw us open it." The physicist said bluntly. The events remained buried in technical reports, with the collider powered off. The world recorded that moment, however faint a scar in the invisible layers of physics. Whether that scar will fade or deepen is a question no one can yet answer. Like, comment, and subscribe for more deep dives into the events scientists won't talk about publicly. And if you think this story ends here, watch the next video. We'll explore the theories about what might have come through CERN's singularity split.